Today, we're interviewing a researcher who studies black holes as a member of the LIGO Collaboration. Dr. Maya Fishbach is a postdoctoral researcher at Northwestern University. Welcome to Bad Astra.
Fine, let's get to the science content.
Why?
We need to talk about polyamory.
Remember when Pluto was demoted to dwarf planet?
It's okay, man. We all make mistakes.
Isn't physics fun?
Is this being recorded?
Hey, Maya, it's good to have you here.
Hi, yeah. Good to see you virtually.
So, can you give me an overview of LIGO in your own words?
LIGO is actually two different instruments which are part of this worldwide gravitational wave observatory. One is in Washington state and one is in Louisiana, so on opposite sides of the United States. It's an observatory, and normally when we think of an astronomical observatory, you're picturing like a telescope, and the idea is similar, but we're not looking for light. We're looking for these gravitational waves. So far, our sources have been black holes or neutron stars that crash together, but you really need something with an extreme gravity, so very massive objects moving very quickly. They emit gravitational waves that are loud enough for LIGO to observe. And the way this observation happens is the L in LIGO stands for laser, so it's pretty cool. We shoot out these very powerful lasers which are measuring distances, and when a gravitational wave passes through, it causes the arms of the detector to wiggle back and forth, and we measure that wiggle with these lasers.
How do you take a wiggle that you've measured and then say, oh, that must be two orbiting black holes? How do you get from one to the other?
The first step is to actually figure out that the wiggle is coming from outer space and it's not coming from here on Earth, because the Earth is constantly moving around, the ground is shaking, clouds are moving in the atmosphere. All of these things are also causing our detectors to wiggle. And so we have like these other channels that are really monitoring what else is going on in the environment. But then also that's why it's really important to have two of these detectors, at least two, because then we can see, okay, it's the same wiggle, that same motion as a function of time, which is this wave, this gravitational wave, in at least two detectors. So we think that it must be coming from space. And then the nice thing about these black hole or neutron star collisions that we're seeing is that we know what that signal should look like. So we know what that wave should look like from Einstein's theory of gravity. And so we look for signals that look like that. And what they look like is this characteristic chirp. So you often hear about like LIGO is detecting these chirps, and that's because the frequencies we're sensitive to are in the audio band. So if you transpose that wave to like a sound, it'll sound like a chirp. It'll be like whoop. If you Google it, I mean, there are like a lot of chirps that you can hear like from gravitational waves where people just like take the signal and put it in the audio band.
I'm definitely going to look that up.
Yeah, you can even make it your ringtone. I think they have like chirp ringtones.
What's your ringtone? It's black holes.
Yeah.
Obviously, you're looking for black holes and neutron star mergers. What questions, like more broadly, what big scientific questions are you looking to answer through LIGO?
First of all, the detection itself. So the first detection of these gravitational waves, that was a huge scientific breakthrough, because for the first time we had this direct detection that gravitational waves exist, and we didn't have like such direct proof before. So just having one detection of gravitational waves from a binary black hole merger shows us that, first of all, Einstein's theory of gravity is mostly right. It's a huge test of gravity. I mean, so far it seems perfectly right. With all of these detections, like the room for any deviations from this theory is getting smaller and smaller, because so far Einstein's theory has passed every test. But we're able to probe that more sensitively before LIGO and the other gravitational wave detector in Italy, Virgo. So these operate as a team. Sorry.
Yeah.
So LIGO and Virgo detected these events. We didn't know that black holes merged. And now we have a lot of these. So
Yeah.
we know that it's actually quite common for black holes to merge. It really tells us about like how stars live and die, because we think these black holes are stellar remnants. So it's a new way to learn about stars. Their afterlives is a lot more exciting maybe than we thought before. It's just giving us this new view into things that are happening in our universe that we'd never been able to see in any other way.
So when someone asks you what you study, you just say, I study stars' afterlives.
Yeah, stellar afterlives.
Could you tell me about some specific recent discoveries that people should know about that are exceptionally cool? And then maybe tell us why they're cool, because, we're just normal mortals.
Yeah, recently, I guess a month or two ago now, we in the LIGO Virgo collaboration released our data from the first 6 months of the third observing run. So basically, we had 6 months of observation between April of 2019 to October of 2019. And those 6 months of data are now public. And in that data, we actually now brought up the number of these mergers that we've detected up to 50 or so. So we now have 50 black hole, some mergers involving neutron stars in the data, and that's really exciting to just have a collection of these. We can really start to figure out like the statistics of this new population out there in the universe. And there have also been a lot of surprises in that data, like a lot of things that we weren't expecting. Black holes that seem to be in this mass range where we didn't expect to see any black hole. Like we didn't think that black holes could exist between like 50 and 120 solar masses, and now we've seen them. And we also didn't think that there would be black holes in between the neutron star masses, which are below 2 solar masses or so. The black hole masses typically start at 5 solar masses, and we didn't expect there to really be anything in the middle. But now we've seen an object that's in that mass range, and we have no idea what it is. Probably a black hole, but we're constantly getting surprised by what we're finding in our data.
So you mentioned two different mass gaps. Could you explain what those are, why you didn't expect to see things in that range, and how science and astrophysics is going to have to change its interpretation of black holes to kind of accommodate these observations?
Before LIGO and Virgo were detecting gravitational waves, we knew that black holes came in all different sizes. So when we talk about the size of a black hole, we compare it to how heavy the sun is. So the smallest black holes we'd seen before were around 5 suns. Within like the event horizon of a black hole, which is the point of no return, you have to squeeze the mass of the sun to like a few kilometers for it to turn into a black hole. So they're very, very small in volume. If I tell you how heavy a black hole is, you then figure out like how big it is in volume. There's a direct correlation between those two. So the smallest ones we've seen are around 5 times the mass of the sun. And then we know that there are black holes as heavy as like 1,000,000 times the mass of the sun. And there are some spaces in between like that mass range where we don't think there necessarily would be any black holes. And the black holes that we're sensitive to with these gravitational wave detectors on Earth, so like LIGO and Virgo, we're only sensitive to black holes that are smaller than like 100 times the mass of the sun and that merge together. So we've seen black holes that are anywhere between like 5 and 30 times the mass of the sun, and then they merge and then they form a bigger black hole. But one of the surprising things from this most recent observing run, so some of the latest data has showed us that there are black holes that are like 70 times the mass of the sun that are merging with other black holes and forming a bigger black hole. And if all of the black holes we're seeing are formed from stars, then we actually wouldn't expect there to be any black holes between 50 or so times the mass of the sun and between 120 times the mass of the sun. And that mass gap is called the pair instability mass gap or the black hole mass gap. And we expect to have that mass gap because the way that black holes are formed from stars is with these supernova explosions. And there's a type of supernova called a pair instability or a pulsational pair instability supernova. We haven't seen many of these. We've seen like a couple that we think are pair instability supernovae, and the theory that predicts them is pretty robust. And what happens is that you have a star that's very massive, so like more than 100 times the mass of our sun. This nuclear burning that's happening in the stellar core becomes very unstable, and the whole star just completely explodes so energetically that there's absolutely nothing left behind. So no black hole at all. And so that's why we expect there to be no black holes between 50 and 120 solar masses, because that's the range in which this explosion is so unstable and so powerful that it completely rips the entire star apart. And now we've seen like a black hole that's right in the middle of this mass gap. So the name of this black hole is GW 190521. That was one of like the most exciting discoveries, is to see this black hole right in this forbidden zone where we didn't expect to see any black holes merging. Either the black hole is not formed from a star, like maybe it's formed from smaller black holes that merged and formed this bigger black hole, or there's something about the stellar theory that we don't understand. And people have proposed that maybe there's new physics happening in the core of stars, like new particles that we didn't know about, that are causing this explosion to act a little differently than we thought.
Which of those two do you think is more likely? Or is that for science to figure out?
There are many possibilities right now. We might not know for like a single event, but we'll definitely have a better picture as we get more and more of these gravitational wave events, because then we'll have more examples and we'll be able to answer this as more on a statistical level. I think right now we're still just hoping for more data, which we'll have a lot more of soon.
One thing I think is fascinating about science and just scientists in general is that you got so excited to be proven wrong. Most people, they really like being right. And that to me is so exciting, that just thirst for like a better understanding that wants to be proven wrong and wants to improve.
Yeah, I think for someone like me, who's also at the beginning of my career, it's much more comforting to know that there's like extra work to be done. Like we're not at the end. So I think especially like after that first discovery of gravitational waves, a lot of people were like, okay, like great, we're done, like we did it. But we just keep getting surprised, and there's like so much more in our data. There's so much work to do to understand what's going on. And so that's like, okay, great. Like I love figuring out what's going on. That just means I'll have more problems to solve.
I love that outlook. Being proven wrong means job security. Bring it back to you and your career. What is your research focus on specifically? You've told me kind of about the big picture of LIGO, but what do you do?
I work with the LIGO Collaboration, and one of the recent papers that I was really involved in is this paper where we're analyzing what we call the population of these black holes. So we now have close to 50 of these mergers in our data, and I look at how massive are these black holes, like how fast are they spinning, how far away are they? So we analyze the gravitational wave, and that can tell us, okay, like how big are the two black holes, how far away are they, and how fast are they spinning,
Can
and
you
where
tell?
are they on the sky?
Okay, so you can tell where they are. So you can basically pinpoint a location within a few orders of magnitude.
So we don't have a very good measurement of where they are on the sky usually, based on the time of arrival of the signal, the two detectors. That gives us like some idea of like if it arrived at one detector first, it was closer to that one on the sky. So we usually localize it to like these rings. The most exciting exception to that is the binary neutron star event from 2017. For that event, luckily, we had all three detectors on at the same time, and we were able to pinpoint it on the sky to a reasonable area that telescopes could actually like point their field of view, which is a lot smaller than gravitational wave detectors. Like with gravitational waves, we're listening to the whole sky like all the time, but a telescope, you really have to like point it to one galaxy. That was like a very fortunate time when we were actually able to localize something to a small field of the sky, because there actually was like all this stuff for telescopes to see too. Typically we don't have a very good idea of where it is on the sky, but we do have a measurement of how far away it is, which in cosmology, the farther away you're looking in the universe, like you're looking back in time. So we're kind of able to see like black holes a long time ago. Now we're actually able to look back to like 8 billion years ago or so. And so we're able to like kind of see how or whether there's like any evolution in the types of black holes we see from 8 billion years ago to today.
And just
So
putting that in perspective, I'm pretty sure the Earth is less than 8 billion years old.
yeah, we're looking like a good fraction of like the observable universe. I mean, something that's really exciting that will hopefully happen in like 10 years or so is we'll get even better gravitational wave detectors, and we'll be able to see the entire observable universe in gravitational waves. Those are the kinds of science questions that I'm interested in. Like, did black holes merge more frequently in the past than they do today? What are the typical masses of black holes? And then like tying that back to like, okay, what does that tell us about the evolution of stars, like what the environments that these black holes formed in, pretty much like how and where are they made, and trying to like tie that picture back with other ways we have of observing the universe, like other things we know about stars and galaxies. Like how can we tie this like additional pieces of information we're getting from gravitational waves back to our understanding of the universe?
How many how many galaxies out are we talking? Like, are we seeing past our own galactic cluster?
Yeah, so we're seeing really far away. There are a lot of galaxies in between us and these galaxies where we're seeing black holes. One thing that becomes like very clear with all of this is how big the universe is. Most things are really far apart. The closest star to our sun is like a few light years away. Most things are very far away from each other, but because the universe is so big, that's why we're seeing like so many black hole collisions. It's not like they're that common. Like in our own galaxy, they'd only happen like once every 500,000 years or something. But there are so many galaxies that we're seeing, which is like why we're able to see so many of these mergers.
I don't know if people realize just how like big space is and just how far apart everything is, but that was a really good visual. So thank you for that. What made you interested in black holes specifically? Like, why did you decide to study black holes?
To me, it's always seemed like very beautiful to try to understand the laws of the universe, and very like comforting in a way to like be part of this. So I've always been attracted to like that mathematical physicsy thinking, and like the theory behind them is also so elegant. It is kind of like art, I think. I don't think of the science questions that I'm doing as being like extremely fundamental for like human survival or anything. It's very much just an extra thing that is fun, and like I think enriches our lives to know more about this.
It's not
So
something we need to live, but it is something that makes life worth living.
yes, exactly.
Like art. Yeah, I like that.
I'm not driven by any application, like any direct applications to our life on Earth. I think it's kind of like an escape often from problems on Earth. A lot of people also find it really cool. So I love being able to like talk to other people about it. I think it really is something that like brings everyone together, some kind of fascination with the universe and like our place in it.
So, what is something interesting that most people don't know about black holes?
I don't know if most people know this, but one thing that I think is really cool just about black holes is when you first hear about black holes, like, oh, they come in all sizes, they can be really small and they can be really big. I think people like get really scared about the big ones. They're like, oh, like a black hole that's a million times the mass of our sun. Like that sounds really scary. But it's actually the small ones that are a lot more dangerous. And this has to do with how big they are in volume compared to how heavy they are. The smaller black holes are like very, very small in volume. So there's like these tidal forces that come into play. Like I think often in popular science, if you read about black holes, you learn about like this term spaghettification, which is when you're close to a black hole, then gravity that your feet feel is so much bigger than the gravity that your head feels, that you just get like stretched out into a spaghetti as you're getting too close to a black hole. So that's way more extreme for smaller black holes. That difference between the pull that your feet feel and the pull that your head feels is just way more extreme. So it's the smaller black holes that are most dangerous. So you shouldn't be afraid of those supermassive black
Hear
holes.
that, everyone? The supermassive black holes, oh, they're nothing. Be terrified of the little ones.
Yeah, the little ones would also be like much harder to detect. So, you know, if you're like actually scared about encountering a black hole in your everyday life, it might be the smaller ones that surprise you. But I mean, don't worry, there are no black holes close by.
That we know of. You just said they were hard to detect.
Well, maybe that's like the one application of my research to everyday life. It's like we are listening for these black holes. So
Hear that,
we want
children? Be scared of a roaming black hole that will rip you apart. So, how did you personally become interested in studying physics and astronomy specifically?
part of it was just having like really good role models. I didn't like grow up always wanting to be an astronomer. I didn't grow up like looking at the stars in the sky because I grew up in Chicago and we don't really see stars very often. I always knew that I wanted to do some kind of science. I ended up finding astronomy professors that I just thought were really cool and that I could picture myself as doing that. And then I just kept going. There have definitely been times where I've maybe reevaluated, like, oh, like maybe I should do something else. But it's ended up working pretty well, and I'm happy doing what I'm doing.
So, you didn't always want to be an astrophysicist. You knew you liked science, but came into it in college.
Yeah, and I think especially with these fields, what I work in now is gravitational wave astronomy, and that didn't really exist like 10 years ago when we hadn't detected gravitational waves yet. You couldn't just like be a gravitational wave astronomer. The most exciting fields are constantly changing, And so it's good to just like keep an open mind and try to be interested in a lot of things.
Yeah, because LIGO wasn't built until what, 2012, 2013?
The advanced LIGO really turned on for the first time in 2015. And there were earlier versions that were less sensitive. So then there were like a lot of engineering done to make the instrument better and more sensitive. And so it really increased in sensitivity, turned on for the first time in 2015, and then immediately, like within the first month, detected the first gravitational wave signal.
So your entire field, like gravitational wave astronomy, has only been around in a big way for about 5 years, and already it's revolutionized astrophysics.
Yeah.
That's
Yeah. And
incredible.
like within my own life, like I entered grad school in the fall of 2015. So it just was like a perfect opportunity. It's a very new field, and I'm also very lucky for the timing.
Yeah, I'll say. Going off that, you're in an incredible subfield on like the forefront of astrophysics, making all these new discoveries. And if somebody wants to do what you do and be an astrophysicist, what advice would you give them?
For people wanting to go into this field professionally, probably for me, the most important thing was to have role models and then to also have a community of peers, kind of just like at all levels, just to have people that you can connect to. I mean, especially if you're like any kind of underrepresented minority in science or like a woman in science or anyone where like you don't typically have a lot of representation. The internet can be a really good place to find role models if you don't have people that are like necessarily at your own institution or within your own immediate networks. But then also to find like other like-minded people that you can connect to. A lot of people think that like physics is so hard and like studying physics is so difficult. I think for me, always like the most difficult thing was feeling like maybe I was the only one who thought it was difficult, and like maybe feeling like, oh, you don't belong here because you have to be like a genius or something. And that's not true at all. And I think like everyone feels that way. And so like being able
I
to
can
find
attest. I did physics in undergrad and it was very difficult.
yeah, I think like everyone feels that way, and sometimes like people might not talk about it. So find people that you can talk about that with and like commiserate with. It's becoming more and more collaborative. And being able to collaborate is like a great skill that's actually valued now more and more. And so, yeah, I think like forming those human connections is really beneficial.
I think the idea that everybody has of kind of the astronomer, like the stereotypical astronomer people have in their minds, is someone sitting alone, thinking really hard, working on a computer or looking into a telescope, very alone and kind of coming up with these discoveries or theories alone, when it really isn't like that, especially modern astronomy. Like, I mean, CERN and LIGO and even my wife's collaboration that she's a part of are so big, and there's so many people from all across the globe. Like you mentioned the Virgo detector in Italy, like there are astronomers around the world all working together, and it's very much a team effort. And I think that part of astronomy just really isn't focused on. And I think that's such a important part of the field, is that it's very collaborative. So thank you for bringing that up.
Yeah, yeah. If it wasn't, then I wouldn't have so many Zoom calls every day. That's that is evidence that it is indeed very collaborative.
Be an astronomer, you'll get all the Zoom calls.
Yeah, even outside of pandemic times, because you will have collaborators like in Australia and in Europe and in Japan.
Yeah, my wife's constantly waking up at weird times because she's got collaborators in Japan, so it'll be really early in the morning for her and really late at night for them, and it's just really cool how you can overcome like time zone, language barriers, all these things to do science, and I think that's really cool. So, do you have any advice for people who are interested in casually learning more about physics and astronomy, especially black holes, in a non-academic setting? So, maybe people who aren't interested in studying physics or people who work in corporate but are just interested in science. Do you have any advice for them?
I work at Northwestern, and the Astronomy Center, CIERA, has a website, sierra.northwestern.edu.
There'll be a link below.
So there's this new Astronomy Live program that some of my colleagues are starting. It'll be on YouTube and it'll be like a live thing on YouTube. For anyone who's familiar with astronomy on tap, it's like the pandemic version of that. So it'll be remote, but there'll be like trivia and astronomers there able to answer questions, and it'll be very interactive. So I think that's like one thing that's really cool. And I'm sure a bunch of other universities have similar things. And there's also on this CIERA website, there's a gallery of like a lot of public lectures and more like outreach based talks that are recorded that you can just watch from home. The internet is just full of like these public lectures and other things that you can watch from home. And that's definitely something that like I used to do before I actually like studied any of this stuff or became a researcher, is just like learn from everything that's available.
And would you say that for most of these talks, you don't necessarily have to have a physics background? Like, if you don't like math, will you still like these talks?
Yeah, I think there are a lot of talks that don't assume any background. Don't be scared.
So, do you have any other shout outs or things you want to promote? Any additional websites people should go to?
I don't know, just want to encourage everyone to care about their fellow humans, support human rights, donate to the ACLU, all that good stuff.
Like that. You
Be
come
a
on,
good person.
you're like, hey, everybody, vote for science, support the ACLU. I love that. While I have your attention, human rights. Okay, thank you so much, Dr. Maya Fishbach, for joining us. Thank you to everyone for tuning into this interview and to our month of black holes. We'll see you next month when our weekly Bad Answers series will return, and we'll be taking a deep dive into vaccines and the science behind their development. Astra out. Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what topic you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring the notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind the scenes, deep dives, and other fun content. A special thank you to all of our Patreon supporters who make these videos possible. Astra out.